Homework solution 2.12. Two loads are connected in parallel to an AC voltage source. Load 1 absorbs real power of 24.96 kW and 47.04 kilovar of reactive power. Load 2 has an impedance of 5 minus J5 ohms. The voltage measured at the load is found to be 678.823 times the cosine of 120 pi t volts. The loads are connected to the generator by a transmission line that has an impedance of 0.01 plus J.1 in both legs. Find the apparent, real, and reactive power at the generator. So if we're to draw a circuit diagram of what was just said in that problem statement, we know that we've got a voltage source. It's AC. It is connected to some sort of load through transmission lines, and the transmission lines have a impedance of 0.01 plus J.1 per leg. So that's 0.01, that's J.1. The same is down here, as they said, per leg, 0.01, J.1. So I think that makes sense to divide it up like that, because the wire connecting the generator to the loads that we'll draw over here has an impedance associated with it. So does the wire that closes the circuit. So if you were just modeling the wire by itself, that's a pretty good way to represent it. It's not how it's usually done though. Usually you just lump it all together up here because the result is the same for the circuit. So usually you just will write J.02. Sorry, not J, that's a resistor, so that's just 0.02. And this is J0.2. Now I've taken care of both the feed and the return. We've got two parallel loads, Z1 and Z2. And we know that the voltage seen across those parallel loads is in phasor form 678.823 over root 2. And we're going to take that as the reference, 0 degrees there. For Z1, we weren't given load impedance directly. We were told that P is equal to 24.96 kW and Q is equal to 47.04 kilovar. We also say it absorbs, so that's inductive, which means it is lagging. That's a lagging load. So kind of an old way to say that, is that it absorbs. Z2, we just know was 5 minus J5 ohms. So that's our givens right there. We're asked to find S of the generator, P at the generator, and Q at the generator. So the approach that I'm going to take is that the total apparent power delivered by the generator is going to be equal to the generator's current times the voltage at the generator, VT. Not complex conjugate, that's a mistake. So I need to determine IT and VT to do this. I'm going to start with the equation for the current. I know that if I combine these two currents here, that's the current being sourced by the generator. So if I can figure out how much current's flowing here and how much current's flowing here, I add the two of them together at that node, that's the current of the source. Another reason to do that, take that approach, is because if I want to know the voltage here, I just have to take the voltage at the load and add the voltage drop across these two elements there. So it's a reason to start with solving the current. So that's going to be the circuit approach that we're going to use. So if we first start by finding I in Z2, which was this 5 minus J5, that's going to be equal to 678.82 at an angle of 0 degrees divided by root 2. And if you throw that in your calculator, you'll find out that that's actually 480. Divide that by 5 minus J5. So V over Z is equal to I, and that gives you a current in this branch of 67.8823 at an angle of 45 degrees amps. It's a capacitive circuit because it's a minus J5. Current leads the voltage. So that's a good indication that we did something right. If I wanted to determine the current in Z1, the two parameters that I know for Z1 are the power that it absorbs, P and Q, and then I also know the voltage. So I'm going to use the same relationship here, but just applied to this portion of the circuit. So I'm going to know that the power in Z2 is equal to Z1. The apparent power in element Z1 or dissipated by element Z1 is going to be IZ1 star or complex conjugate times VZ1. So I can rearrange that and I can say that IZ1 is going to be SZ1 over VZ1 complex conjugate. So SZ1 is going to be 24.96 e to the third. This is an inductive, so it's plus J, 47.04 e to the third. And then I just need to divide that by 480 angle 0. Take the complex conjugate of that, and I'm going to get IZ1. And that gives me a current of 110.941 at an angle of negative 62.049 amps for IZ1 there. I can then determine the current flowing here by just adding the two currents here and here. So I total is going to be equal to IZ1 plus IZ2. And let's just throw these into your calculator. That's 110.941 negative 62.049 angle plus this one here, 67.8823 at an angle of 45 degree amps. And you're going to end up with 111.803 at an angle of negative 26.6 degrees amps. So, as I stated earlier, that gives me this current. I can determine the voltage here by adding the voltage across these two nodes to the voltage drop across this segmental line. So next I'm going to calculate the voltage across that segmental line by by multiplying the current through it times the circuit impedance of the line. So I get VL, which I'm just going to use for line, is equal to I total times the line impedance, ZL. So that's equal to this current here, 111.803 at an angle of negative 26.6 degrees. And then that needs to be multiplied by the line impedance, which was 0.01 plus J. 0.1, I've doubled it here, but remember the original line impedance was 0.01 plus J. 0.1. So if you do that, if you use 0.01 and J. 0.1, you have to sum for 3 voltages. This is equal to that plus the voltage here. If you lump them together, you just have that is equal to that plus that. So using my combined impedance of 0.02 plus J. 0.2, multiply those together, you get a voltage drop across the combined impedance of the line of 24.47 at an angle of 57. Say one thing and write another. 57.69 degrees volts. So that's the line drop across the supply and the return. And so the source voltage, or the total voltage, is going to be the load voltage plus the line voltage. So that's 480 angle 0 degrees plus 24.47 at an angle of 57.69 degrees. And that gives you a total angle of 492.4 at an angle of 2.2 degrees volts. So that supply voltage is a little bit higher because of the voltage drop associated with the supply and the return feeders, which are calculated as V line together. The total apparent power can just be found then from the total current IT times VT, using the complex conjugate of the current. We solve for IT right here, so that's 111.8 at an angle of 26.6 times 492.4 at an angle of 2.2. So we're taking care of the complex conjugate there. And we, after a little rounding, get 55,048 at an angle of 28.8 volt amps. And if I put that into rectangular form, I find that that's 35 megawatts plus 5.0625 megavars. So those are mega, so those doesn't look like it, but they're capital letters, right? So that's our final answer right there for P and Q in the circuit.